let's talk about the mole. Now here's how you use this video. Throughout this video, on the slides, there'll be some text that's highlighted in green. If you're using this to take a notebook, these are the key ideas that you should write down in your notebook. There's also going to be blue text. Now, these are questions for you to answer or questions just for you to consider. Now, throughout this video, there's going to be two codes that are just three random numbers, three random numbers. So one of them is a visual code that'll appear on the screen. One is a verbal code that'll be said by myself. It can happen in either order, so pay attention to get those codes. So let's get started. So before we talk about the mole and what it is, we need to understand a couple things. Number one, the atomic mass. So the atomic mass is the weighted average mass of all the naturally occurring isotopes of an element. So that's, if you look on the periodic table, it's going to be that decimal number. Now the unit is the atomic mass unit, or AMU. So what an AMU is, or atomic mass unit? A proton is 1 AMU, neutron is 1 AMU. Now, you're probably wondering, well, how is it possible that we have a decimal number, right? Now, that's where it comes into play with that weighted average of the atomic, or the isotopes. So remember, isotopes, same number of protons, different number of neutrons. So let's just take a look at this, right? So if I take a look at silver, right? So silver is... silver, right, if I had like a silver jewelry and I randomly picked a silver atom from that, there's about a 50-50 chance that it's going to be either silver 107 or silver 109, right? You can see that's the split. All of them have 47 protons, but different number of neutrons, right? That's what, or not all of them have different neutrons. I got silver 107, silver 109. So I could look at my weighted mass, or the atomic mass is going to be close to 108. And you can see that's where it is, 107.8. Now, you can look at chlorine. It's about a 3/4, 1/4 split, right? Chlorine 35, chlorine 37. So I've got more chlorine 35, so I could estimate and say, well, that atomic mass is going to be closer to 35 than 37. So you can see here it's 35.45. So yeah, it's close to there. Carbon, most of carbon is carbon 12. Right, a little bit of carbon 13, very small amount of carbon 14, so the atomic mass is going to be close to 12. And you can see here, yep, it's like 12.0096. And mercury, you got mercury is all over the place, right? So it takes into account the weighted average of all those isotopes, right? So that's the atomic mass. Now, the formula mass is the sum of the atomic masses of all the atoms in a chemical formula. The unit is atomic mass unit again, right? So it's just like the atomic mass for a compound, right? So you can see here, over here, there's an example, finding the formula mass of C4H10. Great, I just take 4 carbons, or the atomic mass of 4 carbons, and 10 hydrogens, add them together, I'm going to get the formula mass. You might also see this written as molecular mass, right? So formula mass, mostly used for ionic compounds, molecular mass, mostly used for covalently bonded substances. I just want you to know that it's not really much of a difference in how you get there, but sometimes you might see it written differently. So now let's talk about like why we're here, right? Now before we get to that, let's answer this riddle, right? Because this is a great analogy for what we're learning. Which weighs more, a ton of bricks or a ton of feathers? So if we compare bricks and feathers, right? So the first question I'm going to ask you is, what is a dozen? Well, a dozen is 12. Right, just like I've got a dozen donuts, a dozen eggs, right? It's just a number. It's just 12. So now let's answer these 3 questions about bricks and feathers. Which weighs more, a ton of bricks or a ton of feathers? It's the same, right? It's the same, right? If I put a ton of bricks on a scale and a ton of feathers on a scale, they're going to weigh the same amount, 1 ton. Now how about this question? Which weighs more, a dozen bricks or a dozen feathers? So if I were to put 12 bricks on a scale and 12 feathers on a scale, which would weigh more? Obviously, it's going to be 12 bricks. Now, how about this last one? This is a little bit tricky. Which would have a larger quantity of objects? A ton of bricks or a ton of feathers? So imagine you had 2 scales, right? Would it take me more bricks to put onto a scale to get to a ton, or more feathers? You are going to have a lot more feathers to get to a ton. So keep this analogy in mind to answer this question, how big is a mole? Or what is a mole? So the mole is the amount of a substance that contains exactly 6.022 times 10 to the 23 particles. It's just a number. It could be atoms, molecules, ions. You could do donuts, eggs, right? It's just a number, right? Now this number is known as Avogadro's number. So just like a dozen means 12, A mole means 6.022 times 10 to the 23rd. Now, what it does is it helps chemists relate the mass of a substance to the number of particles that it contains. It's basically a way to count something very, way too small to count, right? And we'll get to why it's this number a little bit. But what I want you to see here is a picture of different substances of 1 mole. So in all of these, I have this same amount, 6.022 times 10 to the 23rd. So a couple of them you might recognize. This one up here, C12H22O11. That's going to be like that's a sugar molecule, right? So larger molecule. Well, if I got 6.022 times 10 to the 23rd, it's going to weigh more than like the salt molecule down here, NaCl, right? And you can see here, well, yep, that's small. And off to the right, you can see here I've got sulfur. Sulfur is just 1 atom, right? So it's relatively small compared to that. So I've got a lower amount, but all of these, I have the same number, right? It's just like saying I have a dozen feathers, a dozen bricks, right? It's the same number. Now, they're going to weigh differently, right? That's the key. So here's why it's this number, right? It all has to do with the molar mass. It's the mass of 1 mole of a substance. So if I've got 6.022 times 10 to the 23rd, it is the mass of that. The unit is grams per mole. Now, the molar mass is numerically equal to the atomic mass, or the formula mass, but in a different unit, right? So here's what we mean by that, right? So I have sulfur over here, right? The atomic mass of sulfur is 32.07. Now, if I were to take 1 mole of sulfur and I were to individually count each atom and I were to put it onto a scale, right? 6.022 times 10 to the 23rd atoms of sulfur onto a digital balance, that digital balance would read 32.07 grams. That's the importance of this number. It's a way for me to count the number of atoms in a certain amount, right? Just based on that atomic mass. That's the importance of Avogadro's number. So now let's look at this, right? Let's look at helium versus lead. Now I want you to think about bricks versus feathers when we're doing this, right? So what is a mole? We know what that is. It's just 6.022 times 10 to the 23rd, right? Now let's answer these two, right? Now, which weighs more? A gram of helium or a gram of lead? Now I know weight, I know a gram is a mass and weight, but what I mean is if I put a gram onto a scale or onto a digital balance, right? So that's what I mean. I know that there's a difference there. But, well, they're going to weigh the same amount, right? That digital balance would read 1 gram. Now, how about this one? Which would have a larger quantity of atoms? 1 gram of helium or 1 gram of lead? So if we look over here, you can see here the helium atom is small, right? That's like my feather, right? The lead atom is large. That's like my brick. So think about it this way, right? Would I have to put more of the helium, the tiny ones, on that digital balance to get to 1 gram? Or would I have to put more lead atoms to get to 1 gram? I would have to have a lot more of those helium atoms to get to 1 gram, just like I would have to have a lot more feathers to get to 1 ton. Now let's look at these next two questions. Which weighs more, a mole of helium or a mole of lead? This is just like asking which weighs more, a dozen feathers or a dozen bricks. The lead. If I had the same number of each of these particles, that lead would weigh a lot more than the helium. Now, how about this one? Which would have a larger quantity of atoms? A mole of helium or a mole of lead? Same quantity, the exact same number, 6.022 times 10 to the 23rd. Now, the last two questions says, great, what is the actual mass of 1 mole of helium, 1 mole of lead? You just look at the periodic table. Here it is, right? If I were to take 6.022 and count 6.022 times 10 to the 23rd atoms of helium, put them on the digital balance, it would say 4 grams. If I were to do the same thing for lead, 6.022 times 10 to the 23rd atoms of lead and put it on a digital balance, 207.2 grams, right? That's the importance of the mole. It's a way for me to know exactly how many particles I have just based on the mass. So now let's get some molar mass practice on how to calculate the molar mass of certain like molecules, right? So I'm going to do probably the hardest one here, right? I'm going to do aluminum sulfate here, right? And if you can do this one, you can do any of them, right? So first thing I'm going to do is write down each element that I have in each of them, right? So I've got aluminum here, right? I've got sulfur, and I've got oxygen, okay? Now I need to find the molar mass of each, and I can get that from the periodic table. So if you look at the periodic table, aluminum is 26.98, so I'm going to write 26.98. Sulfur is 37.02, 37.02, and oxygen is just 16, right? Now I need to find the total amount of each of these atoms in this molecule here, right? So I look at the subscript. Aluminum, there's my subscript. I've got 2, right? Now this is where it gets a little bit tricky because sulfate is a polyatomic ion. So if I look at these parentheses here, right, it means I have 3 sulfates. So I multiply the subscript of each by 3 because I have 3 sulfates, right? So I only have 1 sulfur here, right? So 3 times 1 is going to be 3 sulfurs, but the oxygens is 3 times 4. So that's going to be 12 oxygens. Now all you do is you just multiply across, right? So this is going to be 53.96. This is going to be 96.21. And this is going to be 192 even, right? 192. And I'll put 0.00, right? So at this time, I'll go ahead and give you the verbal code. The verbal code is 741. All right, now to find the molar mass of this molecule here is I just add all 3 of these together, and that's going to come out to 342.17. 342.17. So, and that's grams per mole. Now, if you can do this one, you can do the rest of them, because this is the trickier one is with the parentheses here. So there are plenty other ones that you can use to get practice doing this. So now let's move on converting between grams and moles and grams, right? So the molar mass is used as a conversion factor in converting between grams and moles. It tells us the relationship between grams and moles of a substance. So here are the steps. Determine the known quantity, grams or moles, place it over 1, multiply by the conversion factor using the molar mass, and cancel the units and solve, right? So very simple, right? So here are some, and I'm going to do a practice one on the next page just to show you how to do that, right? So here are a couple of examples using carbon dioxide and water. We'll do one with water on the next page. So here are some practices, right? So if given moles, convert to grams. If given grams, convert to moles. And here are 6 problems that we can do, right? I'm just going to help you set up the first 2. So the first thing that you do is you find the molar mass of whatever that substance is, right? So I'm just going to get here. I'm going to do water, right? So the first 2 are water, H2O. Whether I'm going from moles to grams, grams to moles, I have to set it up the same way. Hydrogen, if you look on the periodic table, is 1.01. Oxygen is an even 16, right? Just for the sake of time, I'll just write 16. Now I need to know the number of each. Well, I've got 2 hydrogens, 1 oxygen, multiply across, 2.01, and this is going to be 16. Add them down, well, it's going to be 18 this is 2.02, my fault, 18.02. Right. Now these 2 problems, right, either the conversion factor is going to be the same, but whether it's flipped. This is just like saying 100 pennies is $1 and $1 is 100 pennies. I could put that either or. You're multiplying by 1 basically. So let's just, I'll show you how to set up this first one, right? 2 moles of H2O. So I'm just going to put 2 moles up here, right? 2 moles. I'll put MOL. There we go. Right? So I need moles on the bottom because I need grams. So I'm going to use that conversion factor, right? So one mole of water, right, is 18.02 grams. So I multiply across 2 times 18. That's going to go here, and then it's just 1 mole, and that is going to get me the grams because the moles are going to cancel out there, and I'm left with grams. Now I'll just show you how to set up, let me just erase this here, that could take a while. Let me just show you how to set up that next one, right here. Let me just erase everything, but we'll just remember that it's 18.02 grams. I'll write that here, right? 02, there. So the next one is, well, I've got 36 grams, so I want grams on the bottom. So 1 mole of water, right, is 18.02 grams. The grams cancel out. You multiply, cross, divide. I'm going to be left with moles. That's how you set these up, right? So I did these two. I showed you how to set those up. Once again, you can do the rest. If you can do one of them, you can really do all of them. So once again, just as a final thought, there's too much unknown in the universe to take a break from learning. Get out there and question everything.